all over our slides. We love our orange, because we do work for a Dutch company. And then also some of that development and manufacturing happens just outside of Boston, Massachusetts, in a city called Lexington, which we're super excited about. And then last year we actually bought a company called CoreLeave that also was working on gene therapy for a different neurological disease as well. I'll talk a little bit about the pipeline. So our lead candidate is this program for hemophilia B that actually was licensed to a different company to go ahead and essentially distribute that throughout the whole world. Super exciting for that community, right? Because it was something that had been talked about for about 20 years, and it's actually coming to fruition. And we're really happy about that. And then also, we're starting to specialize a lot more in CNS diseases, right? So Huntington's, frontal lobe, epilepsy, different types of neurological conditions as well. So just to give you a little bit of background as to who we are and what type of work we're doing. Us being here, we absolutely enjoy it. Talking to some of you, listening to your stories, it's ultimately what my job is and what I love doing. And so hopefully in any conversation that we have, we really do try to listen to you all, and then take a lot of those stories that you guys have and help shape internal programs. So when it comes to the impact on our trial, those types of that type of information is super important, having speakers, right? So that way the company knows, hey, like this is the impact of the work that you're having. So whether it's a scientist that's working on some sort of flow cytometry or something like that, all the way to somebody that actually goes out and deals with patients, like our work with you, with the community is highly important. And that I am one person of a team of two. So my manager, Daniel, actually does what I do globally. So I'm West Coast based, which is why, I'm out here. But yeah, we're super excited. If you see us at any congress or anything like that, just be like, hey, you're that guy that had that pose in the picture, and then we'll say yes. But ultimately, our mission really is to deliver one-time treatments to hopefully transform patients' lives, right? That's our goal that drives us. That's part of the work that we do. And we hope to make that, a reality. And it doesn't mean that it's easy, because it's been a long road, but that's what we're here for. And with that, because it hasn't been a long road, we're going to talk a little bit about the history of gene therapy. And again, if we remember at the beginning of the presentation, I said that we were going to be talking about this AAV gene therapy. You'll see that gene therapy actually as a thought or a way of potentially treating something has actually been around for a while, right? And now we actually have gotten a lot better at having the technology to hopefully make that be a way to treat some different diseases. Way back in like 1989, well, I'm having to use a clicker in a minute, so I gotta find, there you go, okay. All right, so way back in 1989, they started really looking at laying the groundwork for what gene therapy was going to become. And in the early 90s, actually, that first AAV gene therapy was done in a different disease state called cystic fibrosis that also has a genetic component to it. And then in about the mid-2000s, there was a discovery, and they figured out that like there's different types of serotypes or different types of AAV vectors, and I'll talk a little bit about that as well, that have certain potential to like be better chosen for different organs in the body, okay? And so that actually started to accelerate things, because it's, oh, hey, we could use AAV and then a number, AAV5, and it works in these specific types of organs that could help treat some of these diseases. So that ultimately led to the first gene therapy product that was licensed in Europe. So that was about 2012. And then here in the US, there was a first licensed AAV gene therapy for the eye that was licensed in 2017. Okay, so now we're actually getting to treatments getting in patients' hands, okay? And then a second gene therapy product was licensed a couple of years after that as well. So now, we are actually trying to make this a reality. Again, it doesn't mean that it's going to happen overnight. It's been a really long road to get to this point, and there's been a lot of setbacks. So I just want to make that clear as well. So ultimately, gene therapy, like I'm going to be talking about essentially two different types of techniques, okay? You can actually use it to have an effect of gene augmentation, right? So we actually want something to increase in the body. I had mentioned hemophilia before. So that actually is like a deficiency in a protein that gene therapy actually increases that protein, right? In the case of Huntington's, you actually want a gene regulate, so actually downplay one of the genes and not have it be expressed as much. This isn't the only types of techniques, right? There's like gene insertion, there's different types of things. But these are the ones that I'm going to be talking about, or specifically gene regulation today, okay? Any questions so far? No? Okay. Okay, so I talked about AAV. What is that? Edgar, I don't understand. I'll try to explain it a little bit better in detail, okay? It's essentially an adeno-associated virus, right? So there are certain viruses that are not cause disease in humans, right? So what ends up happening is we take that viral protein, right? So this protein's outer layer, and then we actually end up engineering a microRNA, so this really small piece of RNA, and then having that to go into the cell and essentially create a molecule that will be constantly produced by that organ that we are targeting, which is why it's important to talk about the serotypes or the different types, because we wanted to have that specific affinity, right, for that organ. Okay, so we talked about the capsid, we talked about the vector. This is just a different way to look at it. So a capsid actually is that protein layer, so the outside. And if you stop by any of the booths, you see that little squishy ball, okay? That's actually what this is. It's just a 3D kind of rendered, like fun little thing. And inside you'll see a little like DNA in it. So that's a 3D model of what this vector ends up looking. So please take one, because there's a lot that I have, and I don't want to take them home with me. All right, so why is this important? And so we know that CAG repeats are a huge portion of Huntington's disease, right? That's ultimately what gives the person a diagnosis of CAG. I'm sorry, of Huntington's. And it really just comes down to DNA. And if you've taken a biology class at some point, there's 4 components, 4 nucleotides that comprise DNA, and then ultimately those code for something in the body for some function, right? And then when there's a diagnosis of Huntington's disease with the increased CAG repeats, we know that there are manifestations within the brain, and that it does start to affect other areas, of function, all those things that we know in Huntington's disease. And so all that happens, right, because there's what we call protein aggregation. So there's a buildup of protein that causes everything to kind of stop. Okay. So you've learned a little bit about uniQure. You learned a little bit about some of the gene therapy and what we're working on. And then hopefully just a little bit of a taste of what a vector is, different components. Like we can get really sciencey, and I try to keep it a little as brief as possible. So if you'd like to learn more, definitely you can come and talk to me about this. Talked a little bit about Huntington's, and then also some of the genetic traits. And then a little bit about gene therapy and what that looks like, for Huntington's disease.
Thank you so much. Does anybody have a quick question that they'd like to? Thank you. Hang on, I'll bring the mic to you. Actually, here. Careful. You
all right. I did not know that was behind me. What was your question?
Well, I'm still not clear how this treatment.
You got a hand up. You got to get it real close to her.
Okay. I'm still not clear. I'm still not clear how this AAV gene therapy is working for HD. And that's because I read the book of Jennifer Doudna, and I think you know who she is. And in her book, she says that for HD, it will be an anti-CRISPR approach to treat it. My first question is how this AAV gene therapy is working, because I'm not clear. And secondly, whether there is what would be a comparison between your therapy and anti-CRISPR? Because I understood from Jennifer Doudna's book that this anti-CRISPR therapy, it's really very promising for HD.
So again, at the beginning of the presentation, there are various methods that are being looked at. This is the first one for gene therapy that is where we're at right now. As the years will go on, there's going to be different methodologies that are going to be different than this, right? So this is just like a first example to answer the second part of your question. So as far as like the effort, it's the vector or the therapeutic agent, that's what I want to call it, is actually put into the brain. So it's essentially this, right? So it's that capsid layer, right? So the outside, and then the little small genome that carries that information, that genetic information, in order to knock down mutant Huntington protein.
Okay, so it's artificial, right? What
Correct. Yes.
I think a few years ago there has been another therapy like that with a vector. So how you are going to deliver it in the spine or directly to the brain?
Yeah. So if you have questions about the clinical trial, we can answer that. But there is an MRI guided procedure that's done in order to deliver that directly into the brain. So.
And which phase are you now in?
So right now we are in a phase 1, phase 2 trial.